Swayam Prabha. Digital India. Educated India.
All right, so there's more to p-small delta effects than just isolating on a member and saying, okay, how can we estimate things with the way we just did with setting up a simple amplifier. This is a frame from the Stability Design textbook by Chen and Liu, 1987. Just a nice, simple L frame where we've got both the column and the beam here have the same length and the same EI. The beam is subjected to a uniformly distributed load, and for purposes of essentially an ideal or an idealized discussion, let's suppose that the column is subjected to vertical load at its top, P, and that P is very large compared to any of the effects from the uniformly distributed load. And so the force in the column, let's say, is approximately equal to P. And so in this case, if we do an analysis of this structure where P is 0, again, W is a very small load, so essentially it's a first order analysis result. And so that what you see here with this moment diagram is what we would have. Again, moment drawn on the tension side. What's the typical practice? In reinforced concrete, I think everybody does tension side, right?
Yeah, mostly people are tension side.
Yeah. And even though I design more steel, I like tension side also, but then I come into contact with people that say your moment diagram is wrong. Anyway, but this is the first order moment. What happens if we start applying axial force here and we keep increasing the level of P? So basically we get second order effects where I suppose a good way to say it is there's the piano string problem. If you take a piano string, you pull it very tight, and you try to deflect the piano string transversely, it's stiffer the higher the axial load on it. Well, this is the reverse of the piano string problem. When you have compression in the member, the member becomes more flexible. And so because of that increase in the flexibility of the column here, we actually tend to get a reduction in the moment at the knee of this frame. Now, depending on the level of load, the slenderness of the members, the maximum moment in the column could be along the length of the column, where you see, as you see in this particular sketch. Typically, it would always be, but well, actually, that's not true. If the load is small enough, it wouldn't necessarily be maximum at the within the length. It could still be at the ends. But you're getting a reduction in stiffness of the column. Your moment diagrams are starting to look like this. And so this second moment diagram is for axial load level between 0 and PEL, where PEL is the Euler load, pi squared EI over L squared. Okay. Now let's take axial force equal to PEL. Guess what? For this dinky little frame here, the moment at the knee joint is now 0. Now that can be problematic if you have a case like this. Let's suppose, again, this is a fairly simplified example, but you could have a situation, maybe a very long column you're trying to minimize the footprint of with an atrium or something like that. But it is taking some moment from connectivity to whatever is up at the top, and so you can have a situation like this one where you may have designed that beam saying, oh, I have in restraint from the column. No, you don't. You just lost it all. Okay? So we often, in a first order analysis of this frame, is, oh, I'm getting in restraint from the column on the beam. I get a negative moment at the knee. I can reduce the moment from my design of the beam. Okay, the column is restraining the beam. But then we do buckling calculations. We say, oh, the beam is restraining the column. We get a K factor less than 1, right? They can't both be true. So this is a situation, at some extremes, you have to be careful with this. You say, oh, this beam needs to be designed for larger moment because of second order effects. The moment amplifier is not going to give that to you. And if you have a design where you have said, oh, this column can be designed based on an effective length factor less than 1, so that means P could be larger than PEL. And so we even have a positive moment at the knee, and the moment within the length of the beam is even larger than the simple span moment. So if we explore this in a little bit more depth, let's kind of look at how this works in the form of a plot. So several curves to understand here. Let's kind of take them in progression with the key there at the bottom of the slide. So the red curve, for starters, this is basically a rigorous theoretical solution. Basically Euler-Bernoulli beam theory, so that this is what we would get in terms of a second order maximum column moment. And so notice that if you look at the horizontal axis of the plot, P divided by PEL, so if P is equal to 0, we've got our first order solution. But that red curve then drops below that solution. We're basically getting a reduction in the maximum moment in the column for as long as P over PL doesn't get too large. But then, okay, if we have very large P over PL, we're going to get some significant amplification of the maximum column moment. Now, the dotted black curve is basically the approximation we were talking about in the last topic. So we can calculate a C sub m for this column. The moment is 0 at the base. The example is for an ideal pin at the base. We've got a maximum first order moment at the top. So C sub m is 0.6. If we calculate an effective length factor for this particular case, we'll look at that calculation a bit later. We get K1 is 0.839. So the B1 equation, basically what we find is until we get out a little bit larger than P over PL of 0.5. So I'll use my mouse here to try to point. So right around here, okay, up to that point, we're basically saying, okay, you just take your first order moment at the top of the column and you use that as your estimate of your maximum second order moment, right? But the real second order moment is actually less. And then once we get higher P over PEL, wow, that's amazing. The B1 approximation is very good for this example. I picked a good example. If we try it for, say, a fixed base with the same loading, we'll say, yeah, it's not too bad, but it's not as good. Okay, so in this particular case, it looks great. All right, now in design, we'll often use just k equal 1 for braced frame. So that would give us the orangish looking curve where we'd get the same effects until we get out to about 0.4 for P over PL, and then B1 would become larger than 1, but it's very conservative because we used k equals 1 in the amplifier. So if you definitely had a case like that, you could get a much better estimate by calculating a k factor and using that in the amplifier. If we consider the blue dash curve, this is the moment at the knee. And so what's going on here? This is what we were focusing on a lot on the previous slide. The moment keeps getting smaller and smaller and smaller as we increase the axial load P until when we get to P over PL of 1 here, the moment is 0 at the knee. So we looked at that moment diagram earlier. And then as we increase P over PL even further, we get basically a reversal of the moment at the knee. And then lastly, the maximum beam moment. That's the green dash curve. So first order analysis would be slightly less than 0.8 in terms of 0.8 of WL squared over 8. But as we increase the axial load, that beam moment is increasing. Now the commentary to the AISC 360 standard has some discussion that's guidance on cases like this. And the discussion is that if you are calculating a B1 on a column, and if it's larger than 1.2, you're advised don't use it. Go to a general purpose analysis to get your calculation. Now at B1 on the column of 1.2 in this particular idealized frame, you can basically see that the amplification in the beam moments are already amplified by 13%. A lot of times in our discussions, some that I'll share with you a little bit later, we'd say, well, we'd like to, for design, be within 5%. If it's research, I'll tell my students I'd like to make sure we're always within 1% with our research solution. But for design, 5% is pretty good. We're starting to be a bit beyond that. When we go to different standards have different rules of thumb like this, where these amplifiers start being not so good. So I noticed some very interesting cases in the Indian standard. Again, I think it's a judgment call, right? So this is a judgment call here, and you say, okay, gosh, that's getting a bit high, isn't it? Yeah, but okay, we'll allow it. As we increase P, the column is getting less and less stiff, right? And so we've got a case basically where we're transitioning from where the column is restraining the beam to where the beam is restraining the column. Okay, and it's that where it's 0 at the knee is that transition point. Yeah, I think the difference from I think you're thinking of the case. If you do it with a spring, you're right. You won't get the 0.
You should not exactly go to 0.
But notice that here it's not a spring. It's a member with a uniformly distributed load. So we're starting out with a negative moment, there at the knee because of that distributed loading on the beam, right? So that's a little bit different than the spring case. That's a good question, though. And so that behavior where it's going from negative moment to zero to positive moment at the knee, it's related to the stability effects, but also related to the uniformly distributed load on the beam. Okay? Thank you. All right, and so there's a slide here that kind of explains all that. The B1 greater than 1.2, then that's the guidance in the AIC commentary. You better start to be careful. You could argue that we're starting to get maybe more error than we would want, even at that limit.